Hey everybody, this is Larry. This is September 12th. In what year is this? 2024. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. Today I'm going to do a random algo problem that I have not solved yet, so let's take a look. It seems like it's called random flip array. When we load, we'll find out. Okay, 519 random flip array. Or flip matrix. I don't know why I said array. It's a long day. Yeah, random flip matrix medium problem 519. Let's see how it goes. Okay, so there's a matrix or zeros. Design an algorithm to randomly pick an index I sub j, I comma j, and flips it to 1. Okay. Optimize to minimize the code to the built-in function and optimize the time. Okay. What is the flip supposed to do? Oh, I see. I see. Okay. I mean, basically you have R and C. I don't know. I just like to keep it R and C. And then here we want to call flip, where you return something that's 0. Flip it to 1 so you don't recur in the future, right? That's the key thing, is that it seems like that's the key thing, which is that you want something that's 0, you do it once and then you go away, and then you have a reset that resets everything. So what I would do is just honestly have yeah, I mean, really there are only two things to do, right, that you can do reasonably. One is keep track of the things that you've already picked, or keep track of the things that you haven't picked, and then do the math on that. How do I want to do it? Because basically, if you keep track of things you picked, reset is easy, right? Because it's just getting rid of stuff. If you keep track of things that you haven't picked, that's reset is expensive, but flip is really easy, right? Because you don't do any dupes. It's 10 to the 4, at most 1,000 cores. But that's the thing, right? Is that's actually pretty. So yeah, looking at the constraints, it seems like you cannot keep track of the non-empty ones, right? Because oh, sorry, yeah, you cannot keep track of all the empty ones, because that could be 10 to the 8, and that's just too high. So the thing to do, I suppose, is, yeah, just keep track of the things that you've already flipped, right? So how we want to do it? I want to say, I'm still thinking it through, like how to do it efficiently, right? Because I think what I want to do is, let's just say, have a sorted list. And the reason for that is that now when we get a one random number, we can maybe do some we can do a binary search on what to return or something. Yeah, I think that's fine then. Yeah. Yeah, let's do that. Maybe. Yeah. So then now let's say we have a sorted list, and I know that oops. But yeah, I know that I didn't explain too much in detail, but we'll go over it in a second. But basically here, maybe we have like a used is you go to a sorted list, an empty sorted list, because we haven't used anything yet. And then reset is easy, right? Reset is just you go to actually sorted list. Or maybe that's clear, right? Maybe that's a little bit faster. I don't know. Sorted list, does it have a clear function? I actually don't know. I mean, I think it doesn't matter, but yeah, no, okay, there is a clear. I think technically initiating a new one is a little bit faster because it uses new memory and or more amortized, but I don't know, this shouldn't matter that much. I think the amortization is the same. Okay, so how do we do flip, right? So here we do want to minimize the number of cores to random, and here we can just have one core, right? Basically, I'm thinking about, but there are other ways to make it so that you could get, you could do this flip thing. But the problem is that it may not be equally distributed, right? Because one idea may be that, okay, if you have, like if you have ignoring the matrix part and just have a linear list for a second, right? You have a linear list. Let's say index 1 is taken, and you flip the 1, then maybe you go to 2. So there are ways to make it so that it goes much faster, but then that's not equally distributed, right? Because then now, if you flip 1, then the number 2 actually has twice as much chance to get picked, because both 1 and 2 goes to 2, right? So there are some like nuances there. I think what I want to do is just binary search for the number. It's a little bit, I mean, we're only doing 1,000 calls, so I'm not worried about it. But basically, because we're minimizing the random function, right? And here we should be able to get, right? So I guess I have to call this on C. So self dot, we definitely need something like this, right? So then here, self dot n is equal to r times c, and that means that now we want a number. We want to get a number from 0 to n minus 1 inclusive, but we already use some of these, so then it's -1 minus u for the number of used, right? So then here we do, I think it's called random dot randint. Maybe I'm wrong. Length of subuse. Let me double check that real quick. Sorry, that was a doorbell. And actually it's like almost midnight here, so people should not be doing it. Okay, so I just want to check whether this is inclusive. I was relatively sure about it. It's free to check, especially. So yeah. Okay, so this is the random int, and we just want to get, basically, we want to get the off number. But the thing is that here, some numbers are used, right? And we don't know which one. So to get the, we know which ones, but we don't have a way to do which ones quickly. So the way that we can do that is by using binary search, right? So basically, we're guessing. Okay, we're guessing. So so we're searching a number between n or 0 and n minus 1 inclusive, and then one of those numbers is exactly our off number, right? So then we can do that. So then now, if so self.use.bisect right mid. So this is basically the number of numbers that are strictly that are mid or smaller, right? So the number that are mid or smaller, if that is less than r, then we want a bigger number, right? So left is equal to mid, else right is equal to mid minus 1. Maybe if it's equal, okay. Maybe off by 1 here, but okay. So if r is 0, then this number and if there's nothing used, then this number would keep on getting bigger. So that doesn't make sense. So I think I need this actually. Because if it's equal, then we want to try something smaller. Okay, that makes sense. Yeah, and then now, left is going to contain the number we care about. And I think I skipped a little bit. Sorry, I'm trying to solve this problem to make sure I don't get it wrong. But the thing that I'm doing now is actually I kind of lied about this being a matrix. I just converted from a matrix to a 1D array of r times c length, and then now we just do a random number from 0 to n, n minus 1, sorry, and then now we could convert that number back to the r and c, right, which is going to be so left is going to contain the thing, so then now it's going to be just left. I think as long as we're consistent, it should be fine. Right, row. So that means that for each column. Okay, so something like this. Yeah, maybe I'm wrong. Wait. Okay. Ooh, is it not sorted containers? Oh, containers. Eh. Wrong answer. Oh, definitely. Oh, yeah. I'm being silly. I forget to put the left in used. So yeah, so that used not left because it was doing the same thing twice, or 3 times even. Wow, that is really bad luck. So it was really bad luck, or my math is really bad. Yeah, maybe I'm off by. Am I off by? I think this is the thing that I'm worried about. But okay, let's see. Maybe I'm just doing the same thing for some reason. Okay. Well, that's definitely not what we want to have 2s. Why is that? Okay, so here we have all left used. Maybe I'm off by 1 somewhere. It's okay. So the R is going to be 2 from 3 elements. Okay, we added 2. The R is going to be 0. 0, right? Okay. Okay. I think my binary search is wrong. Is the answer. So if there's 0, I think okay. We want to get the off number. All right. Let me. Sorry, I have to reset my brain a little bit. I mean, I think the idea is right, but I'm implementing it really. I think I inverse the function. Is what happened. And what I mean by that, instead of getting the off number, we get the number in which whatever. So okay, so basically, yeah. Basically, yeah, I'm asking the wrong question. This should be like, so basically, this contains the number that are smaller than mid. So for mid to be the off number, so okay, so let's say. Oh, let's actually take a look at it. So we have R is 0 to 0 twice. I mean, it makes sense because we already used the other 2. So that means that we want the new 0th number. Okay. So, but that doesn't mean 0 numbers are smaller than it. How do I get that? Maybe I'm just doing wrong in this binary search. If I want the smallest number, okay, I see. If I want the smallest number, then I have to choose. I have to find the number of numbers that are available. This is the number used, not the number available. So okay, so that means that I actually want mid minus this. I think. Okay, yeah. Like I said, I got it inverted, I think, at some point. But honestly, I think I was just rushing it a little bit as well. And this is why it's important to test and also sound out what you want to do, right? Yeah. I think this is a little bit slow just because of, this binary search and this. But can I be a little bit... I mean, the thing is that we're trying to minimize we only care about minimizing the number of calls to the random function. At least initially. So we definitely did that because we only have 1 call per flip. Now, can we optimize this from n? So yeah, for number of flip, it's going to be n, because this is a log n call and this is a log n loop. So this is going to be like n log square n. Can we reduce this further? Because honestly, the first thing I wanted to do is just get it to be correct. Giving 1,000 cores, I wasn't really worried about the running time, but the complexity is different, right? And the distinction is that, you know, we just don't have that many cores, but it doesn't scale as well. Oh. Yeah, I mean, the easier way is to initialize everything, but can I do an implicit initialization? I don't think so. Not easily. I mean, there are other ways to do this. Are they all log in? Because I think maybe we can take advantage now, because indexing is yeah, because you could do some kind of like repeated doubling maybe, but I think indexing is still log in, so I don't know. I'm curious how people do it. Yeah, I mean, I guess this is the other way, but that does not minimize the random, right? So that's why, I mean, yeah, I think it depends on how you want to say it. Maybe it is luckier, I don't know. How does this work? I mean, this like seems like it's my idea, but without the binary search with x is map.getDefault. I don't know what this means. Oh, that's clever. They don't explain anything about this, but this is basically Fisher Yates. That is actually very clever. I'll explain this one because that is clever. That is, yeah, wow, huh? Yeah. And because the way that I was thinking about it is that I couldn't do it without initializing all the space, but basically what they did was doing an implicit Fisher Yates, right? That is a beautiful code. That's a beautiful idea. Yeah, I mean, I think I could implement this actually, which is, I'm going to implement it real quickly just so that I confirm to myself that I understand it, and then we'll go over the code or go over the idea. Actually, I think it's beautiful, so I think it's worth doing it. But I want to confirm to myself that I understand it as I think I do. So yeah. Yeah, maybe just this. I think there's a get default in Python, right? Then it returns none. No, it returns key not found, right? But oh yeah, that get not okay. Okay, so then now we want, what do we want to do? Right? We want to get the number u, and this is now self dot. Now it's just yeah, okay. Yeah, maybe I'll keep track of count. Right, so then now that's just self dot count increment. And then now what we want is, that is, yeah, oh, that's a good one. I'm actually, for once, I'm glad that I actually looked at the thing, because usually it's full of crap. But and hopefully, you know, you're watching me live, so you're watching my thought process when I read these things as well, because everything is live. So I mean, obviously, or maybe it's not. I don't know, whatever. But okay, what am I doing? Okay, so I get a number. Oh, it should be afterwards. And then that number is what we want from the lookup, where the default is itself. And then we swap it with the last count, which is this number. Yeah, and then now we want to just, well, we don't care about this, and then now we just do something like this, and then now this is just self.look. Empty range for 0, 0, n minus what? Self.n is right. Count should be 0. Am I doing something wrong? Leave that here for a second. Okay, so that means that I do it. Oh, because I'm dumb, because the reset, we have to reset. Okay, I mean, clearly we should not have -1, but why do we have -1? Yeah, this number got incremented as well, so we need to put an increment here. But also this change, we want the original thing, so it's this thing. So then now we want x is equal to this thing. I'm being sloppy because I'm just rushing it slightly. Let's give a quick submit. Okay, so yeah, I mean, I love this solution, by the way. I mean, I didn't come up with it clearly. Maybe I could, I don't know. I think maybe if someone told me that it could be done, maybe I could have come up with it, but maybe it would have taken a long time, honestly. It's something that I don't think this is to my strength, so I don't know if it would have taken a while. Or like it would have taken a while, but I don't know if it would have taken any faster than a while. So okay, so how does this work, right? Instead of going over the code is not that important, but let's go over the idea of Fisher-Yates, right? The shuffle algorithm, you may know as. But the idea here is, who is ringing the bell at midnight? My apologies. Hopefully it's not too loud coming through the mic. But I don't know who's ringing my bell. Probably just drunk people, honestly. It's Friday/Thursday. In any case, so what's the idea about Fisher-Yates shuffle, right? So the idea behind Fisher-Yates shuffle is that you have an array. So let's just say we started off, you know, in order. Oops, how did that happen? I don't know how to write anymore. And then the idea here is that with Fisher-Yates, and there are a couple of variations, just to be clear, they all do the same thing, so it doesn't really matter as long as you're consistent about it. And so basically, with this number, we want to place going from right to left, right? We want okay. Let me try again. Going from right to this is all from memory and live, so if I'm missing some stuff, my apologies. But just to kind of give you a taste of how this is related, right? But yeah, going from right to left, we start with this number, right? And this number, we go, okay. It could be any one of these 8 numbers. So okay, so then we set it. So maybe the number is say 6, right? So then now we set this to 6. Maybe I like another color. That doesn't. Yeah. So then now we set this number to 6, right? Say, and then here we put an 8 here, and then now we move to the next index. And what does that mean, right? Well, what happens is that now another way to think about it is that this 6 got taken out the rotation, right? because then now we know the last number is 6. Then, but here we still have 1 in 7 chance of getting every remainder number. So, and you can prove this inductively, right? So that's basically the idea. And it's very easy to kind of miswrite the Fisher-Yates in a wrong way, such that you don't get perfect distribution. But here, but the inductive idea, and I'm doing this not in an induction way, but but the idea behind induction is that, okay, well, for the first number, you have 1 in 8 chance of picking any number. You swap it, and then the 8 is here, right? So then now, looking only from the left side, because then everything to the right side is done. Everything to the left side, everything to the left side could be 1 out of 7, and everything to the left side could be picked. So let's say we picked a 3, right? So we picked a 3, so then we swap them. So this is now a 7, this is a 3, right? Even though the 7 is here and this is in some funky order, everything to the right is done. Everything to the left has same equal distribution of being picked, right? So that's basically Fisher-Yates' idea off my head. So, like I said, if I'm missing some critical details, let me know in the comments. But yeah, that's the idea. So how does this relate to this problem? So recall that when I was first saying that I thought that like we can keep track of the things that we have used, but it would take too much space, right? Because R and C could be 10 to the 4. So we initialize basically this array. Even if we had this array, if we initialize this array, it would be 10 to the 8, right? But what I was going to do something simpler than this, so I wasn't thinking about this idea yet. But okay, again, for now, right? I know that this problem calls for a matrix, but the mapping from a matrix to 1D is pretty straightforward, right? Just like every line by line thing. And so the idea here is to use a sparse, by using a map lookup, we're having a sparse array. So, and by sparse, we basically just have a whole array where if it's not, if this slot is empty, we just assume that it is the the number, right? So for example, yeah, these are all good, but if this is a 7, then we actually store the 7, right? So that's basically the idea behind this thing, and we just get it one at a time. So now we always take our RNG number from one of these things, and we don't care about the stuff that we already used, and we can only pick stuff that is free. So that's basically the idea behind this in a Fisher-Yates kind of way, and it's very beautiful. I think. I mean, it doesn't come up that much in competitive programming because it's a very specific idea. With like usually, like in competitive programming, it doesn't come up. So maybe I don't get this much practice. Is because you don't have these weird constraints, right? Your constraint is just usually if you have a linear time thing, then a linear time thing is going to be good enough, right? Like, and even honestly, n log n is probably going to be fast enough for most of the time. So it's very hard to enforce an O of n thing, which this thing is. Like I said, because O of n is just so much easier as well. So I don't know, but it is a cool idea, and kind of maybe now you see how why I I think it's a beautiful idea that you just kind of Fisher-Yates it. You take a random number from the stuff. And now you can think about count as the stuff at the end that we kind of don't just leave and not touch. And here, we just get the current value. This get is basically if it's empty, meaning we haven't said yet, we just return the number R, because basically that's the sparseness part of it. And then this is the swap we swap the last element because that's the element that's getting removed into here, and then now we get the last element basically, which is going to be whatever we fetched before, and then we just can well, this comment is not true anymore, but yeah, and then we just kind of convert it back to 2D thing. Yeah, a beautiful idea, very cool idea. I'm glad that I kind of randomly stumbled onto that one. Yeah, hopefully that makes sense. But that's all I have for today. That's all I have for this one. Let me know what you think. Thanks for watching. Yeah, stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.